Angular momentum, will give that the general symbol for angular momentum is L. It is a vector, right? A vector that is produced by the cross product of a displacement vector, how far out from the center, the origin you are, multiplied by the linear momentum. Do a cross product of two vectors, you get another vector perpendicular to those. That would classically be your angular momentum. There are all kinds of angular momentum, orbital angular momentum, spin. We'll see what exactly we mean by spin. It's a little bit different than the other ones in quantum mechanics. Rotation is a type of angular momentum. And then since they're vectors, you can join those together as well. You can couple them. You're going to see that all of these different angular momentum follow the same eigenvalue algebra. So let's look at a general angular momentum. Well, think of it, as orbital angular momentum, right? Of a single electron. Single electron, so we're going to use a lowercase letter to denote when we're talking about a single electron, uppercase when we're talking about a system of coupled angular momenta. The operator operates on a wave function, and if that wave function is an eigenfunction of the operator, you'll get an eigenvalue. And in this case, the eigenvalue we're going to call m sub L. The natural units of angular momentum are h bar, right? There's always going to be a magnitude and a z component that we're going to specify, right? So if we're looking at the z component of orbital angular momentum operating on some wave function that denotes, for instance, an orbital, then what we'll get is m sub L h bar times that original wave function. Then, apart from the component where it points in space, we also have the magnitude. The magnitude will use an operator like this, L squared, operating on a wave function is going to return, and we're going to see this over and over again, L times L plus 1. L is a quantum number that's going to be positive. M sub L can be negative or positive or 0. L can also be 0, but not negative, right? And you'll see that we're going to have these magnitude and projection quantum numbers that we're going to deal with over and over again. Very interesting property of angular momentum is that they have very specific commutation rules. You can specify only certain aspects of angular momentum. No two components of angular momentum can be specified simultaneously. Only one can be. And that one component that we're going to specify, we're going to call the z component. Now, the operator for that z component of angular momentum, when we express it in polar coordinates, it's a very simple operator, minus I times h bar times the derivative with respect to an angular variable, phi. The operator for the magnitude of the angular momentum is we have to sum the square of the three components, the Ly, Lx, y, and z components, or if we put that in polar coordinates, which is going to be much more useful for atomic and molecular systems, then we transform it into r, theta, and phi. And oh, look, the magnitude only depends on these operations in the angular variable, the Legendrian operator, we'll call it. Now, remember, in quantum mechanics, the order of operation is important. So if we're looking at this term over here, right, what do we have to do? First, when you take this term and you're going to operate on a wave function, first you take the derivative with respect to theta. Then you'll multiply by sine theta. Then again, you take the derivative with respect to theta before dividing through by sine theta. All right, so you have your wave function out here. You're going to operate from left to right. You do this one first, next, next, next. Always make sure order of operation is important when doing operator algebra. The commutation relations, I mentioned these, right? You can't specify any two components, but you can simultaneously specify one component, the z component, and the magnitude, right? These two operators commute. They have a zero commutator, and therefore the magnitude and one component, the z component of angular momentum, can be specified simultaneously. Therefore, these two quantum numbers, that is the quantum number for magnitude and the quantum number for the component along the z-axis, those two can be specified. They're well-defined or good quantum numbers. We can define them and their value simultaneously because both are eigenfunctions of the wave function of the system. So we can specify, for instance, for orbital angular momentum, both L and m sub L simultaneously. If we were talking about rotations, we would be able to specify the magnitude of rotation, which goes with the rotational quantum number J and its component m sub J. Or if we were looking at spins, we could specify both S and m sub S. That, very rapidly, is our introduction to angular momentum. All angular momentum obey the same eigenvalue equations, the same eigenvalue algebra. Magnitude squared equals J times J plus 1. H bar squared would be our units, right? Projection m sub J times H bar. No two components of angular momentum can be specified simultaneously, but you can specify both the magnitude, J, and the component, m sub J, at the same time. So those two are good quantum numbers. We can specify them and the values they have simultaneously, right? Exactly.